Welcome to videos on linear integrated circuits. In this video, we shall see CMOS operation amplifiers. So, in this particular video, we shall see the Bode plots of amplifiers. So, the references for this particular video is Alan Holberg, which deals with CMOS analog circuit design. So, let us consider a first order amplifier and its Bode plots. So let us consider an amplifier block diagram. That is, so this is amplifier 1 having a open loop transfer function A1 divided by 1 plus S into tau 1, where tau 1 corresponds to the time constant. So now since it is first order, we have only one pole which is located at minus 1 over tau 1. Now this is the Bode plot of this amplifier having a transfer function A1 divided by 1 plus S into tau 1. Since we know that this is a first order amplifier, the Bode plot, that is the magnitude plot and phase plot, is plotted over here. So as we know that we have only one pole which is at minus 1 over T1, which is the location of the pole in terms of S plane. The cutoff frequency of that pole happens to be 1 over tau 1. So you can see now this is 1 over tau 1. Now till 1 over tau 1, the amplitude of the amplifier will be constant. Afterwards, it decays with a slope of minus 20 dB per decade, and it is passing through this 0 dB line. The frequency at which this magnitude plot crosses 0 dB is nothing but omega GC. We call it as gain crossover frequency. And we see one more plot which is the representation of phase of this amplifier having a transfer function A1 by 1 plus S into tau 1, varying from 0 to minus 20 degree, and its phase is minus 45 degree at 1 over tau 1 frequency. And we have a frequency which is omega GC defined as equal to omega at magnitude becomes 0 dB, or magnitude is equal to 1 volt per volt, and the phase is given by minus tan inverse of omega tau 1. As the value of omega changes, the phase of this is keep on changing, and we're going to have maximum phase of minus 90 degree as omega tends to infinity. So this is the magnitude and phase plot of this amplifier as the frequency varies from 0 to infinity. Similarly, let us consider a second order amplifier and its Bode plot. The frequency response of that is both the magnitude and the phase plot of this amplifier having two poles. One is at 1 over tau 1 and 1 over tau 2 are the two cutoff frequencies. Now, as we can see from the magnitude plot, the magnitude will be of constant amplitude of gain A2 till 1 over tau 1. We are assuming 1 over tau 1 happens to be the first pole frequency, which happens to be the dominant pole now in this particular case. Now, till 1 over tau 1, it will be having a slope of 0 dB per decade. Afterwards, the slope will be minus 20 per decade till this frequency, which is 1 over tau 2. After 1 over tau 2, this again starts with a slope of minus 40 dB per decade. So this A corresponds to minus 20 dB per decade. This B corresponds to minus 40 dB per decade. And here also, if you can see here, this magnitude plot is crossing 0 dB at this frequency. This corresponds to omega GC. Now this is a phase plot. So as we know that the phase equation is given by minus tan inverse of omega tau 1 minus of tan inverse of omega tau 2. Now these two are the two pole positions replacing S by j omega. We can write the phase equation as given by these two terms. As the value of omega changes from a low frequency to high frequency, the phases keep on reducing from 0 to minus 180 degree, and there's a maximum phase of minus 180 degree as omega tends to infinity. So as omega is tending to infinity, the maximum phase we're going to get is minus 180 degree. So let us consider a third order amplifier and its Bode plot. Since we know that since there are three poles, so till a frequency of 1 over tau 1, it will have 0 dB. Afterwards, it is minus 20 dB per decade till 1 over tau 2. After 1 over tau 2, the slope is minus 40 dB per decade till 1 over tau 3. After 1 over tau 3, the slope is minus 60 dB per decade. Now this is how the slope of the plot changes from 0 dB per decade to minus 20 dB per decade after 1 over tau 1. After 1 over tau 2 it changes to minus 40 dB per decade. After 1 over tau 3 it changes to minus 60 dB per decade, and it goes with the same slope till the omega is equal to infinity. So we know that the phase equation is given by minus tan inverse of omega tau 1. As per these three terms, we are going to have three terms corresponding to the phase. So one corresponds to the first pole, which is which is having its time constant as tau 1. The second pole has got a time constant of tau 2. The third pole has got a time constant of tau 3. Corresponding to each of the pole, we are going to have the phase representation by each one of them is minus tan inverse of omega tau 1 minus tan inverse of omega tau 2 minus tan inverse of omega tau 3. Substituting the value of omega from 0 to infinity, so we're going to get maximum phase as minus 270 degree at omega tending to infinity. This is how it is, phases keep changing. It is 0 degree and it is goes towards minus 180 minus 270 degree at a particular frequency. So this phase crosses minus 180 degree, so that is called as omega pc, which is equal to that value of omega where the phase is minus 180 degree. So we define one more parameter now, phase crossover frequency. Phase crossover frequency is that frequency where the phase of the system, phase of the amplifier is minus 180 degree. Now let us consider a first order system having a transfer function which is 1 over, which is given by a by 1 plus s tau 1. So we have written the magnitude plot and its phase plot. So this is 1 over tau 1. As you can see now, the slope is minus 20 per decade. So there is a omega gc. Now you can see the phase plot shows that maximum phase is minus 90 degree only. So that will going to occur at omega is equal to infinite. So at omega is equal to omega gc, so let us assume that the phase is given by phi of omega gc. So this phi of omega gc is the phase of the plot when omega is equal to omega gc. So we can define one important term in the case of amplifiers, which is called as phase margin. Phase margin is now given by the expression 180 plus phi of omega gc. Now since phi of omega gc corresponds to the phase at which it corresponds to the phase for a frequency of omega is equal to omega gc. As we know that since omega gc can never be lesser than minus 90 degree, so we're going to have this omega gc maybe around minus 80 degree, minus 55 degree, minus 60 degree. So always this phase margin happens to be positive in nature. We'll consider a second order system and try to find out its phase margin now. So as we know that in the previous case also, how far away from this minus 180 degree, so we have a minus 180 degree line here, how far away this omega gc is from minus 180 degree corresponds to the phase margin. This is minus 180 degree line and this is the actual omega gc uh, actual point where a phase corresponding to omega gc is there. So this is called as phase margin. Similarly, we have a second order plot. So we have a plot of second order system with a pole at 1 over tau 1 and 1 over tau 2. Their cutoff frequencies, this is minus 20 per decade, this is minus 40 per decade, those two are the slopes, and this corresponds to the gain crossover frequency. So corresponding to this frequency of omega gc, so we are having a phase which is given by phi of omega gc. Now here also we can find the phase margin. Phase margin is again it is positive. So phase margin is given by 180 plus of pi of omega gc. Since pi of omega gc may be around minus 150, minus 160, minus 170. Since 180 minus of 160, 180 minus of 150 happens to be always positive, the phase margin of a second order system is also positive. So let us consider a third order system here. Now we have considered a third order system having three poles with time constant tau 1, tau 2, tau 3. So as we can see now, there are three changes in the slope. This is from 0 to minus 20 dB per decade. This is minus 20 to minus 40 dB per decade, minus 40 to minus 60 dB per decade, and it is crossing uh, the 0 dB line at this point, which is known as omega gc. The corresponding phase is given by pi of omega gc, and it is interesting to know that since there are three poles, it's a third order system. The phase changes from 0 to minus 270 degree. We're going to have omega pc also. The previous two cases of first order and second order, we didn't had omega pc because the maximum phase was only minus 180 degree in case of second order system, that was reaching at omega is equal to infinity. In the first order system, minus 180 degree was not at all being crossed because the maximum phase that we're going to get here is only minus 90 degree. So only in case of third order system we're going to have omega PC here, that is the phase crossover frequency. So we have a phase crossover frequency. So let us try to find out what is the magnitude of the this magnitude plot at omega is equal to omega pc. So we know that this is a of omega pc corresponds to the magnitude at a frequency corresponding to the phase crossover frequency. So we have a frequency which is omega gc, corresponding to which we have a phase, and we have a frequency omega pc corresponding to which we have a magnitude. So let us try to find out. So from this you can see that in this particular example, omega gc is actually smaller than omega pc, or omega pc is actually greater than omega gc. Now let us try to define what is this phase margin now. Now we know that this, since omega gc is coming before this omega pc, this phase happens to be something like minus, so this can be, so you can think of this as minus 150, minus 160, so on. So since it is minus 160 or 150, so the phase margin happens to be positive. Now you can see phase margin is 180 degree. This is actually 180 degree plus of phi of omega gc. So phi of omega gc maximum can be minus 270 degrees. So whatever we have here, so this can go up to minus 270 degree. That is, phase margin can be negative also, because this phi maximum can be up to minus 270 degree. Here there is a possibility that this phi of omega gc can be more negative than minus 180. When it is more negative than minus 180, the phase margin becomes 180 minus of, assume that omega phi of omega gc is minus 220 degree. If it is minus 220 degree, then phase margin becomes minus 40 degrees. So that is what, if omega gc lies between minus 180 and minus 270, then the phase margin is negative. And if omega gc lies between 0 and minus 180 degree, then phase margin is positive. Meaning, if your omega gc is lesser than omega pc, we'll have this condition, that is phase margin is positive. Suppose if omega gc happens to be coming after omega pc, then we have omega gc will be satisfying this condition, then we have phase margin which is negative. So let us also see what is gain margin. So gain margin is nothing but minus of magnitude at omega is equal to omega pc, or it is given as 1 over omega pc in volt per volt. So as we can see now, this is omega pc, corresponding that we have a magnitude here. So this magnitude may be, since it is 0 dB, so this may be minus 20. So assume that if A is equal to minus 20 at omega is equal to omega pc, then gain margin happens to be minus of minus 20, which happens to be 20 dB.